Hi, this is Rob Bolaños. Welcome to the analysis design of a flyback in video 33. The subject is going to be thermal analysis. Okay. I'm using a different computer. I just got a new computer and trying to learn how to use the software itself. And I'm switching from journal to X journal. Hopefully this will work a little bit better. For some reason the journal kept crashing in the middle of doing the video, so hopefully I won't have problems with this. So bear with me. There's a learning curve still with this. Anyway, the thermal analysis is a very important subject, and typically if you're a electrical engineer, once you do your design, you want to make sure that your power devices can survive and operate within your environmental limitations or specs. So when you do the analysis, you want to calculate your junction temperature of your devices. What kind of devices? Well, we're talking about your diodes, any transistors, MOSFETs, and even integrated circuits. Okay, so we'll give a demonstration later on. Okay, and the other that I want to address is this is kind of a follow-up to video 32. In video 32, I use a one of the flybacks, and I had mentioned that if you use the wrong turns ratio, that the reflected voltage back to the drain of the MOSFET would lead to a hot MOSFET. Okay, and I think I even said that if your MOSFET gets hot, it's going to get destroyed. Okay, so in that video, it was just a statement. So I'm going to try and use this video to demonstrate how to model it and basically prove that the MOSFET would get destroyed. Okay, so this particular video is an important follow-up to video 32. If you haven't seen 32, please watch 32 before watching this one. Okay, so now one of the terms is what is the thermal impedance. So I'm going to go ahead and define that a little bit later. And then what I want to do is I want to show how we can model a thermal system and then use it in SPICE. Okay, so instead of doing the paper, we're going to go ahead I guess the calculations, we can model it and we can use SPICE to calculate our TJ, okay, which is your junction temperature. Okay, now usually when you do thermal analysis, that's in the domain of the electrical engineering folks. Okay, so when I do a design at work, I do my electrical design and then I calculate my power of the devices. And then I give my electrical guys a list of all the parts, basically all the parts, and what is the power dissipation. And they typically do a model, but we can do some of this model Okay, do like a first order pass, and instead of working in their domain, which is a mechanical domain, where they use power, transfer, thermal impedance, and temperature, and here are the units: power, watts; thermal impedance, Celsius per watt; temperature, Celsius. Well, these actually translate into the electrical domain. Okay, so this is where the electrical engineers operate in the electrical. So we're very good at this. This is where we specialize. Okay, so when we're talking in power in the electrical domain, well, that translates to current. So when we use current, we use a current source to show that it's a power dissipation. So if we put 1 amp, that's really 1 watt. Okay. And then thermal impedance is Celsius per watt. In our domain, we use a resistor, R. Okay. So that we can do it in SPICE. This we can do it in SPICE. And then temperature, they use Celsius, but we either use the voltage at a node, or we can use, to set the temperature, we use a voltage. So that would be 12C. We actually use a voltage source. Okay. So that's what I want to make you aware, that we can go and do a little bit of a thermal modeling using these terms or these symbols. Okay, so here is the definition. Okay, I wonder if there's a way of setting the zoom. Let's see how this works. Okay, I think I like that a little bit better. Okay, so here is the definition. In this case, I'm using the thermal resistance from the junction J to A, ambient. So this is from junction to ambient. Okay, and typically the equation is the temperature of the junction, go ahead, of the junction minus the temperature at ambient divided by PD. This is the power dissipation. Power dissipation. Okay. So let's take a look at this and see if we can make it a little bit more intuitive. Okay. Well, this power, here's a representation of this equation, or at least what they mean to each other or how they relate. Okay, so this power is this power. Okay, we'll go ahead and say PD. So it's a, and remember PD is in watts. Remember, this is Celsius, watts. Therefore you have Celsius divided by watts. Okay, so you have heat being generated, and it's going to be generated within the silicon device. Okay, and remember, this is kind of like a MOSFET, so this is a cross section, and you can think of this as let's say sitting on the plastic case. So heat is being generated here, and that heat has to, typically it moves from hot to cold. Okay, so the heat is generated in the silicon, and right at the silicon, that's where your junction is. Okay, so the junction has a certain temperature. Okay, and typically TJ max, let me reframe. Some of the TJ maxes that I'm aware is anywhere from 150 C's. And I think they've seen them to up to 175 C's. And on some of the other devices like silicon carbide, it may go even higher. But anyway, so as you generate, that heat is going to go to the colder side. So this is hot. This is cooler. So the heat transfers or wants to go in this direction. Okay. And as it goes in this direction, the temperature, the delta, gets cooler. So then at this point, if you notice this is TC, that's T to the case. I'm sorry, it's to the copper. Okay. In this particular example, they're using the copper. So there's a delta temperature. From here to here, there's a delta. Okay. So this delta would be the delta junction to the copper. Okay. And then it goes from the copper to the case or the heat sink. So you have another from CU to case. And then from the case, typically it goes either to the board or to ambient. So board, or it could be ambient. So at every stage you have a delta. Okay, so each stage is represented by a resistor. Okay, so this is representing from the junction, TJ, junction. Okay, it's going to have a certain voltage, and that voltage is equal to a TJ, a certain temperature junction. Okay, and then this node is the temperature at the copper. Okay, and then you have a resistance that represents the thermal resistance from the copper to the case. Okay, so same, you're going to have a certain voltage here that represents the temperature at the copper level, and then the voltage at that node is a voltage which corresponds to a temperature at the case, and so forth. So this is the model that you use, that you can easily implement in SPICE. Okay, now I want to point out something. Okay, if you notice this here, these are capacitors. Okay, and those capacitors are used to model the thermal mass. Okay, so basically they kind of store the temperature. Okay, just as in electrical they're used to store uh, temperature or voltage, you can store temperature. Okay, so what does that mean? Well, if the temperature goes up, it doesn't go immediately up. There's a little bit of a rise time for the temperature, just like in voltage. Digress a little bit. So as in voltage, you start from zero in the capacitor, and then it goes up to steady state. Same with temperature. Because you have a thermal mass, instead of the temperature going straight up, it rises exponentially, just like an RC circuit. So these are thermal masses. Okay, and like so, there's a certain time constant. A thermal time constant is associated. Constant. Okay, so we got that. Okay, so I think. Okay, now in the last simulation, I showed that I used a IFR 150, and I have the data sheet here, and some of the parameters that you need to look for and that you need to be aware or you look for is TJ. This is the operating junction temperature. In this case, it's going to tell you the range. So you can work anywhere from -55 all the way to 150 volts. 150 degrees Celsius. So this is your TJ max that this device is rated. Okay, so then another thing that you can see here is your thermal impedance or resistance. Okay, and mind you, it's called thermal impedance because you have complex. In other words, you have the thermal resistance, and then you have remember the capacitance, the thermal mass, so you got the T mass. So that would be kind of like the imaginary part. Okay, so in this case, this R theta is the resistance. Okay, in this case, this is the number that we want to use, especially if we're going to mount it, let's say, to another heatsink or to a board. Okay, so that's the number. Now typically this number, if I'm not mistaken, on some of the definitions that I've seen, they put the device on a 1 inch by 1 inch. They power it and they take the temperature. Okay, so you don't have any basically way to eliminate that current or that power or that heat. So this is basically junction to ambient. In other words, just regular air or your ambient. Okay, so this is the one that you want to use. Okay, so now I want to bring up something that I'm hoping to discuss a little bit later on some of the other videos. Derating. This is something that's very important for power engineers. Okay, you need to be aware when you do the design, you have to derate your devices, and this includes diodes, capacitors, resistors, and so forth, and more importantly, your devices. So So in this case, here we go to, this is the transistor derating requirements, and this I believe is from either a IEEE or a JPL derating guideline. I don't remember where I got this, but anyway, if you notice, it says junction temperature and it says derate to 80%. I believe this is 80% of your TJ max, I believe. Okay, but if you notice, it says a 2. That's node 2. Okay, so in this case, the note says that you want to derate to 125 degrees or 40 below the manufacturer's maximum rating, whichever is lower. Okay, so let's see if we can do it like a little example from that. So here from the IRF 150, we know that TJ is 150, and we're going to use a R theta JC of 0.83, which is right there. Okay, so we got that. So the TJ derated, in other words, this is the limit that we, or the maximum that we want to limit. In other words, if our design goes over this limit, you fail the derating. Okay, so in this case, it's either going to be 125, or in this case it's TJ max minus 40. In this case it's 150 minus 40 degrees is 110, and it says which pick the one that is lowest. So in this case, this is the lowest. So our TJ derated should be 110 C. So we want to keep under this number. Okay. Okay, so now let's go ahead and see if we can model it. Okay, this is the wrong schematic. Let's see if we can find. Oh, by the way, this is a high voltage pulsar that I am presently working on. Let's see if we can go to the proper. See, which one was it? Oh, thermal hot. Okay, so here is my switch mode power supply that I simulated in the last video, and let me go ahead and I guess I'll just leave it like this. Okay, so what I want to do is, I had made a statement that if you left or you did not select the proper turns ratio, that selecting the wrong ratio would overheat this MOSFET, and it was kind of a little bit of a hand waving, and this is a way of proving what I had said was correct. Okay, so let me go ahead and select the proper turns ratio. The proper turns ratio is supposed to be 12 volts divided by 24 gives you half, so that's the turns ratio. Okay, so this is a proper one. So by adding this device, this is a voltage source that is dependent on the current measurement and the voltage measurement across the MOSFET. And what it does, it measures the voltage across the MOSFET and the current V and I, and it multiplies it. So basically your voltage times your current will give you a power. Okay, but in this case, instead of a power, it converts it into a current source. So let's say if you have 1 amp and you put a 1 ohm resistor, well, 1 amp times 1 ohm gives you 1 watt of voltage, or in other words, it would give you 1 volt. 1 volt means 1 watt. Okay, so this is a current. So basically that is this here, that section. This is the current source, is that. Okay, so then we're going to go ahead and select this. This is the theta JC, and let's change that to 0.83. Okay, so this theta JC would be that resistor. And then in my case, on the particular boards that we do at work, we have measured that we have a theta from the case to the board of approximately 10 degrees. Okay, so in this case we will use a 10 ohm resistor. Okay, so then this would be the board. Okay, so this voltage here is the temperature of the board, and let's assume that the board is at 25 degrees C. So if you want to make the board 25 C, then we have to set this voltage at 25. So we'll do 25. Okay, so I think we're set up. So we'll go ahead and run it. It may take a little bit of time. Oh, and what I did is I added a capacitor here because that's supposed to simulate a thermal mass, and basically the capacitor actually also averages the temperature. Basically, since this is switching on and off, okay, since it's switching on and off, remember the power is V times I. So the power, if you were to plot it, looks like this. Basically, when it's conducting, and then when it's turned off, you have 0 power. So when you put the capacitor will average this. Okay, so that's what you really want. You want the average temperature. At steady state. Okay, so let's see, and if we look at the temperature here, okay, This is showing the temperature of the junction, which looks like is 30 degrees. So I only went about 5 degrees above that. Okay, so I have that there. Okay, now let's take a look now, and let me go ahead. I noticed that I have this at a different temperature. I was taking the, you can also do this model for a diode. Let me go ahead and turn off the temperature of the diode, because I don't want to confuse anybody. Okay, and let me go ahead and save this. Basically, I want to turn this off, that, and I just want that. Okay, let's see if I can save it. Save. Okay, so we started at 25 room temperature and it's about 30. So that's good. So now let's go ahead and, instead of, we'll leave it open. Okay, so now let me change the turns ratio to a voltage. Okay, so now changing the turns ratio of 0.1, and you might want to watch the previous video in case you're a little confused why changing the turns ratio, or lowering it, would make this device fail. Okay, so I've already changed it, so we're gonna go ahead and run it. And instead of displaying all of this, let me comment it out. You just put a little star and it will not plot that. Okay, so we run, and I think we got everything running. And I do want to show that some of the manufacturers are already including this type of models in their devices or data sheets. So I'll show one of the companies that is doing that. As in fact, I'm working with one right now on my pulsar. I'm using some GaN FETs from GaN system. I'm using a 650 volt parts, and on that one the model, or the thermal model, is included in their LT Spice, P Spice netlist. Okay, so now if you notice, look at the temperature, the TJ. Okay, the maximum temperature that we're allowed is 110. If you look here, look at that. It's way. As a matter of fact, the steady state is going to be 300. At that point, I think the solder would probably melt. Okay, so there's a difference. See, and if you notice, the voltage doesn't even go up to 12 volts. Okay, because the voltage at the drain is being clamped at 100. And remember, when you decrease the turns ratio to 0.1 or decrease it to 0.1, the drain wants to go to 150 volts, but because the 150 is 100 volt, it doesn't allow the output voltage to go up. So that's a big, powerful tool to have in your tool chest, learning how to do that. Okay, so I want to go ahead, last thing, I want to go ahead, go to GaN systems. Okay, this is some of the devices that I'm using. Excuse me. I'm using this particular. Okay. And let's see. I believe I saw. Let's take a look at this. This is the LT model. Okay, it tells you the level. There's 3 levels and they each predict. And if you notice this one, level 2 and 3 has a thermal model. Okay, and there's a way that you can set the thermal. Here it is. See? So this is built into their LT spice model. Okay, and then if you take a look, I believe they may have the numbers here. At least I thought I saw them. Maybe not. It may be in the P-Spice one, but they do have the values of these right here. And I believe if you were to add from Junction to the case, these add to 2 degrees per watt, if I'm not mistaken. Okay, but anyway, so that's the model that I want to show. That it is something that is being done on some of the newer manufacturers, and it's a powerful tool or skill set for you to understand this and be able to model this. Okay, if you have any questions or comments, feel free to email me at rbola35618@aol.com, or you can post your questions here on my YouTube channel down below. Thank you for watching. Oh, and if you found this video useful, please share it, subscribe, and give me a thumbs up to at least give me feedback whether I'm doing a good job or not. Thank you for watching.